Okay, this is part 2 of the piston tutorial that we're doing in class. This is where we got up to last time. The one other thing that we're missing here in our piston tutorial is we need to do the liner, which is also going to be simulating the overall engine case for the sake of these drawings. So we're just going to use our sketching tool, make some shapes. We're going to use this surface over here. I want that outside ring. Okay, got the shape here. We'll just make the liner also slightly larger. Size, it doesn't matter. So it's two things I want to do with this liner. One, we want to, we didn't do the inside sketch, did we? I'm going to make this to a certain height. So we can do that. And just for the sake of this sketch, I'm going to do this at half, just so we can see inside our particular object. So I'll cut it in half like this. So that's our liner, new body, wonderful, yes, good. The next thing we need to do is we also, because this is going to be the engine block, this particular component is the piston's going to go up and down this liner, but also the crankshaft is going to be rotating about it as well. So we're going to be making something that's going to something that's going to go down to where the crankshaft is. And we want it to go through that. And just for the sake of this, we want to hide the crankshaft, piston, all that stuff. But we do want to join it to our original piston and liner, this shape over here. Good. And then we've got to do the hole where we want the crankshaft to be. So what we're going to do is we're going to use our combine tool. We're going to combine the original, this is our target body. We want to, that is our tool. And then we want to use the cut. So we're going to cut that hole in our crankshaft. And we want to keep the original tool because we do want to keep the crankshaft. And then we have it. So now we have, that is the liner and the hole for our crankshaft to rotate around. So this is all we need now to start doing our animation or to do some motion studies for this particular part. The way I found to do this, there's a dodgy way and there's a clean way. The clean way to do it is we like these individual components we have here. They all look nice. We can change all these into individual file names that we can later combine together. And so how we're going to do that is we can say I want to, so file, I want to make a new part. Let's say a part design, create new. And this part I want this to be the piston from our example that we just did. So we'll go here, find year 6, sorry, stage 6, this one I believe, no, which model are we on? The 1.1. I think it's this one. No, that's not it, it's the other one. Yep. Save and continue. So now we're choosing which bodies we want to use from this design. And let's say we just want the piston for now. And then we press OK. We have that piston and see how it's a new file over here. We can then save this, and we're going to save this as stage 6, 2026, 2026 piston class example. Yeah, 2026 piston CE for class example. We'll do that. Save. And then we just do that with all the other components. Let's make a new thing again. Create new, insert. Have recent, so this will be the one. And in this next we want the let's say for this one we want the wrist pin and the connecting rod. We do not want the piston for this case. Untick the piston. We just want these two, and we can see over here that these are the two that we're going to get. We're going to get just the wrist pin and the connecting rod. For this argument's sake, we're going to have them combined together. And then we can save that. 2026. What do I call that part? The connecting rod, Conrod, class example. Save. And then the last two we have is we have to do the liner, so we'll do it again. Oh, that one. We don't have to hide them. So we just want the crankshaft. We do not want the connecting rod, or we don't want the wrist pin. We just want the crankshaft. And then let's check over here. We just have the crankshaft. '26. And then we have one more now. We just got to do the liner. The liner, but we call it the body. We can actually call that the liner. And if we select that, oh, did we lose it? And the liner, the last one. So now what we've done here is we have made what we've done here is we've gotten the big object we had with all the piston, line arm, crankshaft, whatever, all together, and we've made them all into individual components. In the real world, you might do these, you might do individual components first, but I find it's when I'm building them together, especially when I'm making up dimensions for how things look, I like to combine things together here and then separate them later, because I can still change things. Like I can change diameters of one particular part here in the master, and then it will change all the other individual files because they're all derived from that original file and dimensions, like with this hole over here, for example. So now what we're going to do is we're going to make an assembly. So we'll make a new, we'll do an assemble design, create new. And now we have to insert components. So press this insert component thing. And if we look at our stage 6 engineering, we should have under our recent parts, we should have the liner. Now, can I multi-click this? I cannot. Okay, we'll do them one at a time. We can add the liner. The crankshaft. Are we missing? Why are we missing the crankshaft? Is it hidden? Ah, it's just hidden. We have the crankshaft. It may because it was hidden in the original document. So we just got to check that when we add our Conrod might also be hidden. No, it's not. So there's our Conrod. And then our last one is we'll add in our piston. So now we have all these components in and they're all individual parts here. Now we can tell this because over here we have this little color on the side. This means that this is telling us these are all different files that we're connecting to. Because sometimes you're going to have the same file used multiple times. Like if you have an O-ring, you don't need to make a new file of the O-ring. You just use the same O-ring 20 times. It's going to be common if you have nuts or bolts, or if we're doing this, if we do a 4-piston setup, we'll use the same piston 4 times. And so you can tell at a glance which file you're using by the color over here, if it matches. So what we want to do now is we want to make these all connected together. So when we move one component, they all move together. So how we do this is we use our, we're going to be using our motion and we're going to make some joints. Not drive joints, relationship joints. So in our joints menu, the joints are very iffy. I like to save my work before I do my joints and do them one at a time if you're not comfortable with them. I did an example like this earlier, so I think I'm okay with it, but I'll still do it step by step. This will be the motor 2026 whole motor assembly with joints. Save. So the first thing I want to do is I want the piston and the liner to move. Before I do this, I actually want to make sure over here, the reason why I added the liner first is the first object you bring in by default gets this little anchor symbol over here. So what it's saying is in our assembly, everything is going to be relative to this. We do not want this thing to move. This is going to be they use the word grounding or an anchor. Everything is going to be moving relative to this. So that's why I like to make sure the first thing I add into my design is the thing that I want everything to be relative to. So that's why we did the piston. That's why we did the liner or the engine case as the first thing we imported. So the piston moves up and down the liner. So we're going to go to motion. We're going to relationship. We're going to go to joints, and we want our piston to move relative to our liner. So how we can do this is as we hover our mouse over the object, we can see we get some options. You get a surface that shows up, but you also get these little dots and stuff. So what we want is we want this thing, the piston, to slide up and down this tube. Does it make sense there? So if I hover my mouse over, what I'm gonna do is I'm gonna hide the things that I don't need. So it's going to remove some confusion. And as I bring my mouse over here, I want to do this rotation. I want that tube, and those are my 2 things I want. As I click those 2 options, and right now, if I have this selected as the motion is rigid, I don't want rigid. What I want is I want to slide. I want the piston to slide. That is not the right direction of sliding, but it is how I want the piston to slide up and down there. And I want it to slide in the y-axis, but it's rotated for some reason. So let me cancel. Let me try that again. Let's go with relationship joints. Before I do rigid, I'm going to press the slider under my motion. And now I want this. As I bring my mouse over here, I'm able to select this part. So what I'm saying is the outside of the piston is what I want to slide, and the axis I want it to slide up and down is the center axis. So I bring my mouse over here, and I want it to move up and down that. I can do some limits on it, but I can see that's the action I want. I won't do the limits yet because I don't think that matters, but let's just bring it down there for now. And if I press OK, so if I actually animate this joint, if I right click and I animate this joint, that's the motion that I want the piston to do. I can do the limits later, but that's what I want the piston to do relative to the liner. Okay. Now it's got to go to the process of linking the parts of it together, like the song you had in kindergarten where the hip bone's connected to the knee bone or whatever. I don't know. I'm not a doctor. We got to do the individual parts of the piston as they're connected together. So we have the liners connected to the piston's connected to the wrist pin, but in this case, the wrist pin and the Conrod are the same part. So we're just going to connect the piston to the wrist pin. So for this one, let's hide the liner and let's hide the Conrod. So we just want, sorry, the Conrod is what we want to connect. We want to hide the crankshaft. So the only way these are connected is this pin is going to be connected to this hole over here. So we're going to do the same thing. We're going to go to motion. We're going to go to joints. This time, we're going to use not a slide. We don't want to slide. We want it to be able to revolve around that. It doesn't matter if the pinhole moves up and down because the Conrod's pinhole is also matching that. But what is going to matter with them is they're going to rotate relative to each other. So which is called the revolute tool. And we'll pick this surface over here. We want that surface to revolve relative to this. And that is not the direction we want. Cancel. So if you're we want this tube to rotate relative to that tube over there. As you hover it, we want here, but we also want to select this dot that my mouse is trying to do there, and notice that disconnects. What you can do in Fusion is if you hover over the surface you want, and then you press the control button, it allows you to move your mouse now to pick where you actually want the axis to rotate around. So we want this point over here. That is our point, and this is our other one. And now those two should rotate relative to each other, and we'll press OK. Unhide, unhide. So now, and we can test these two. We can right click and animate this joint. Yep, that's what we want. That's the motion we want in general. Okay, press escape. And we're going to do the same thing with this one down here. Relationship, joints. Over here, revolute. Yes, same thing. We want that to revolve relative to that. Those two, okay. And the last one is we have this hole over here, and relationship joints revolve. We want that to revolve relative to that. Cancel. What's happening? One thing with the revolve tool is it does want to force those two to be lined together. So what we might give it is we might change it to a cylindrical joint instead. That might give it that option to move if needed. Okay, we press OK. Now all these parts should all be connected together now. Just to check, we've got the liner connected to the piston by a sliding, then we have the piston connected to the connecting rod by a revolve, we have the connecting rod connected to the crankshaft, by a revolve, and then we have the because it would be slightly out of alignment, we have then the crankshaft connected to the liner by circuit. So if this all works, we'll save our work. And then now that we've saved our work, if we go and if we rotate this joint over here, we'll go to our relationships, we'll open up our joints, and we have our 4 joints over here. If I go right click on this slider, and if I press, I don't want to actually do that. What I want to do is I want to revolve this one over here. So I want to press animate joints, and oh, so if I animate joint, just that's going to happen, which I mean, that's not great. What I want to do is I want to right click and I want to animate all the relationships. And does that work? It's not. Why is it not working now? Um, Something's trying to happen. Let me see this. Okay. What if I slide? What if I lock the slide motion? So we don't want to slide, we just want it to rotate. What if I do this now? Ah, nice. Now that I press animate joints, now they're all rotating together and we get that lovely looking animation, which is perfect, right? That's the perfect animation we want. They're all working relative to each other. Wonderful. So why do we bother doing this? There are some reasons we wanted to do this, more than it just looking pretty. Actually, as an animation tool, it's not that useful because it's not going to give you like the rendered images you want to do that. You want other 3D software to do this. But where it is relevant is we can do motion studies with this. We can do motion studies, and but what I like to do, let's say I want to find out how much, if I do a rotation, how much my piston liner has moved up and down, because that's where we can find things like our compression ratio, which has been, the topic in Formula One this year of the cars can only have a 16-to-1 compression ratio, but some of the people are finding ways to do 18-to-1. So how do they find this compression ratio? The FIA, they doing tests there, they would have certain degrees for where they're testing their pistons, because it's not as simple as ours. This is more complicated, but they would say a particular angle. So at this particular angle, which I can do things. How do I do my motion study? Motion study. Okay, I can do motion study over here. I think I can slide this joint into here. I can click this joint over here in my motion study, and I can say I want to add a point over here. At this point, I want it to go at 90 degrees. Right? And then at this point over here, I want it to be at step 40. I want it to be at 180. Right? So fairly simple. If we animate that, we should see it's just going like this. Right? It's fairly fine. But what this allows us to do is we can look at individual frames, and let's say at this frame over here, 20. At this particular frame over here, we know that the crankshaft is at 90 degrees. We can do things. So if we go here, we can find out. We can't find out our volume per se, but what we can do is we can do the measuring tool. We can say how far away is this from here, and then we measure that as 35.021 or 30 from the center. And then we can go to our motion study. Or did we lose our motion study? That's annoying. So that's at 180, and then we press OK, and now we can measure it over here. And this one is at 40. So we just get the difference between those two, and we find out how much volume, how much we've moved up and down. We get those two lengths, and then we can times it by the area. If we go and we inspect, and we find this over here, we can even find our area. So you find your area by your height, you get the compression values. You know how much compression your thing has changed. Also, what's relevant is we can do things like we can, when we rotated this at, if we rotated this cylinder at 90, press OK, we can do things like we can find out what our angle is. We can go to our inspect tool and we can find our angle there is like 22 degrees, which could be relevant because that means our force is going to be, when our piston is pushing down, our piston's pushing down vertically, is going to be like a 22 degrees of a force that's going not in the direction of the piston line, it's going to the side. So that's going to cause things like buckling, and knowing that side angle could be relevant. So as we make our piston longer, that angle will reduce, but then we're going to add more weight. Speaking of weight, other things we can use fusion for. We can do things like we can actually do a body analysis as well. But we can do this outside of our jointed system now. We don't really need that for here. Oh, the other thing we can do in this rotation is we can do like a contact analysis. What is it over here? One of these things, interference. We can see if objects are touching each other. We can see if there's some sort of a collision happening, which there shouldn't be in these because we designed all these together, but that's another thing you can use CAD software for. So let's go to the example where we had the Conrod. Because the Conrod is something we already tried to start drilling some stuff out to save some weight. So with the Conrod, we can do things like we can right click this part over here and we can press properties. When we press properties, we get some things. We get area. Area is not really relevant, but I guess if you have a complicated body, your surface area could be relevant. If it's you need to paint it, you know roughly how much you can use surface area as an approximation of how much you need to paint it. If you have something that needs like a chemical reaction, as you know, like if you're generating rust or you're making something that needs a chemical reaction, that's usually related to surface area. Or something like heat dissipation is also something that's usually related to surface area. This material is steel in our example, but we have our volume. So once we have our volume, we have our mass, 2.71 grams. And so as we make some adjustments in this, we can change that mass. We also have like where the center mass is as well, relevant a lot for aircraft. Specifically, you can calculate your center of mass. We also have stuff like our moment of inertia, which we knew we needed for our buckling equations we were doing before. Or if we have to upset start to rotate, we can do that. And Fusion CAD in general allows us to easily calculate these. These are all calculations we can do by hand, especially if we simplify it, but it makes it very easy to put together. I like here in CAD software, we can both easily find the inertia based on the center of mass of this particular object, but also the origin. As the object moves, its location is it's rotating itself. So if you think of an airplane or a Formula One car, the piston itself is moving up and down, so it has its own inertia to matter with that. But also as the car is moving left and right and the plane's rotating, that also is going to change that inertia. So we also want to start doing some simulations. So let's go here and we'll go to simulation. And we'll do stress tests. We'll set up the simplest of simulations. We'll do like a buckling test of this thing being pushed down. Now, the first thing I'm going to do for this case is I'm going to simplify by removing this pin. So I'm going to press the simplify tool, and under simplify, I'm going to just do the wrist pin. I'm going to right click that and just remove. So it doesn't remove it from the actual design, it just removes it from the simulation. So when we do our simulation, we want the parts to be as simple as possible and only get that information out of it. So we have our object over here. The constraints we're going to set up is we want this bottom part to be fixed. This part is not moving. And then we want our load. We want our piston's going to be pushing our pin down. So basically, it's going to be rotating this circle. And we want this to be rotating downwards. So we'll press the Y, and let's just give it 1,000 newtons, negative 1,000 newtons. So we see here this arrow shows that it's pushing down. There's a downward force of 1,000 on this particular pin. Technically, this is not fully correct because it's actually going to only be half of the pin is going to be feeling the downwards force. But right now, in this simplification, the whole pin is being pushed down. These are part of the trade-offs you have to do with doing a simulation. You got to know what you're actually doing your simplifications with. And if I just press the solve button, yep, thank you. We should get a solution out for this. I'll just press solve. And it shouldn't actually take that long because this should be a fairly simple one. And if you have the student account of Fusion, it should just go to the website and start printing this out for free. And if we press this tab over here, we can see what's happening. It's sending the model. There you go, the model's been uploaded. I think I'll pause it and I'll review it when this is done. So the time right now is 12:32, so we'll see how long it takes. All right, so we're done here. It only took a minute or so. So we'll press close and we'll go and we'll look at the results. Now, I don't like how they've done their new results with this current version of Fusion, is they really tried to simplify it. Fusion will always by default do a factor of safety analysis, which means that you have to be realistic with the forces you're doing, which I guess is good if you're doing a bridge or whatever. If you know your actual forces you're putting in, it's quite good because it'll tell you whether your part's going to break or not. But we don't actually know what the forces of a piston inside a motor is. I'm sure we can find it out, but in our case, we don't. So this is very over-engineered, this particular part. 1,000 newtons. A piston that is that big could easily handle 100 kilos being put onto it. But what I prefer to do is under the studies, press the results over here, and it gives us all these other options that we can press. So I like to go to the stress over here and just press von Mises stress. And what it's going to do is it's going to show where the most stress is in our pinner, because this will show us where we care the most about where it's likely going to fail. And so you see here we're blue, and then we have the most over here. We have like the most stress over here. So in our example, this tells us as the engineers, this is where the most stress is. So if we're up to our design limit, as we start weakening this component, saving weight, this will be the part that's going to have the most stress. So this is going to be the part that's most likely going to crack or buckle first. Okay, so let me show you examples that I was doing. Let me show you examples that I was doing previously, so I don't have to load all the renderings. Is it this one? So I've done some examples of some studies. What you can do in CAD is to answer those particular questions is we can do things like thermal studies. Now, I don't think I did the thermal study correct. So take this with a grain of salt. Watch yourself. Okay, we don't care about this. Just show me the video. Oh, it doesn't like something like this. Simulation results. For some reason, the thermal one isn't really showing, but we'll get to that later. So when I did my part over here and I put some stress on it, this one I did it at the angle because I wanted to see as the piston was at like that 45, at that 90-degree mark. and it's happening at an angle. And we see when we change the angle, the stress is not over here, isn't where the most stress. The most stress is actually over here. So as our piston is cycling in its rotation, the location where the highest stress is changing. So it's fair to say, as we're rotating the piston, it's experiencing some sort of cyclic stress. So that's going to be causing an issue. What else do we have? Is this thermal one going to show an answer? Probably not. I think I did the thermal one. I was showing the whole piston and liner. So I don't exactly know how to do the thermal one, but you can find out how the heat is dissipating throughout the object. This one, it all ended up being the same temperature, which makes me think I made a mistake with this one. It didn't work. This one over here, I did the whole piston and liner, or as much of it as we had in our example. And we see in our simplified version, our piston over here, this is angling. Now this looks bad, but because that looks like it shouldn't actually happen, right? But we have this option over here. We have adjusted. What adjusted does is it forces the deformation so you can visibly see what's happening. But if we do the actual deformation, the actual deformation is nothing. It's basically unrenderable because it's so small. And in fact, if we go to this thing over here and we actually go to displacement and do total, right? The total displacement is 0.003 millimeter, which is basically invisible to us. But when we press this one adjusted, it's saying do it until we can actually see the issue. All right, so that's actually what's happening. That's adjusted. So keep that in mind as you're doing there, like what's going to be happening on like a atomic level. Now, the other ones I had here which were interesting is which one? The frequency study. Maybe do I have to resolve this? But okay, I've lost it. Let me redo this particular study. So I'm going to do let's go to new. I'll just do a new study. So I've got a new study. I want to do a modal frequency study. So it's good for seeing vibrations, which is obviously relevant for a motor. So over here, we are going to press can we just solve it straight up? So the modal frequency is, so in like music and in science, you get those tuning forks and you bang them and they do a certain tone that comes out of them. Every object has a frequency which it naturally resonates at, and you can use the CAD's very good at finding that software for finding that out. It's a function between its orientation, its size, but also the material that's inside it. Once this is complete, we'll see what the modal frequency of the connecting rod is, and what that means is if our motor or if our components, if anything is moving at that frequency, it's going to be causing a lot of stress on the component. It's going to basically the damage on it is going to come out exponentially because it's not able to dampen that. So any energy that's going to generate that frequency is going to go to exciting that particular component instead of actually going to where you want it. In a car, in the case, is to the wheels. All right, the design's been finished and we're just receiving it back now. Let's see what happens over here. Something happened over here. Didn't like this result. Because I didn't put any. I needed to put the constraints on it. Constraints. Let's say I want this fixed over here. Now let's solve. So we've got the thing over here. We see over here 2040 hertz. I believe we can even animate it if we want to see what that vibration looks like. So it's vibrating like this. We can change that speed to be fast. Okay, vibrates, go. Right, that's a vibration. And we can see the mode over here. So 2000 hertz, 7000 hertz. So that's vibrating in that direction, left to right. So what this is relevant, 2000 hertz. That's if we get to 2000 frequency, 2000 times a second, the energy is going to go into this. So, well, that's 2000 hertz, which is times a second. So if we times it by 60, that's 120,000 RPM. Formula One cars get to about 60,000 RPM. But we can see if we pick a weaker object like an aluminium thing, we might get into a range that will be relevant. So that's why we can use this as simulation. Thank you.
So